Hey guys, so in the last video we explored the concept of a derivative, which is one of the main operators in calculus. And so now I want to go a little bit deeper into it and looking at some of the rules when evaluating a derivative. Now we saw that there was the difference quotient and you could take the limit of the difference quotient, right? But that is not the best way to get especially a complicated derivative. So now I'm going to give you a few nice rules that you can use when trying to differentiate something. And differentiating is just taking the derivative. So the first thing is, and don't mistake this with what we had in the last video with the partial derivative. That was just showing that t was a constant, right? But if I've got two functions of x, got two functions of x and I want the derivative taken of their product, right? So I want the derivative of f of x times g of x. That's multiplying. So how do I do this? Well, there's a rule. It's called the product rule, and I'm not going to prove this to you. There's a nice proof that you can use involving difference quotient to show that this is actually a property of derivatives. But for right now, you can go with it. I've got in the description, I will have some links in proving the product rule. But if I want to take the derivative of f of x times g of x, what I do is I take the first f of x times g prime of x. So first times the derivative of the second plus g of x plus the second times the derivative of the first. So plus g of x times f prime of x. Remember, f prime of x is the derivative of f. Right, so it's first times the derivative of the second plus the second times the derivative of the first. And you can actually use this to prove the constant coefficients rule that we had in the last video by letting f of x be a constant. And so then we know f prime of x is 0, and so this is just a constant times the derivative of g of x. All right, so now we have the quotient rule. And now you might wonder why we need a separate product and quotient rule, because if we're dividing, right, if we have dx of f of x, actually I'll write it a little bit like this, of f of x over g of x, right? But I want this derivative, right? I could say that this is the derivative of the product f of x times 1 over g of x, right? And because this is just, right, this is what a quotient is in terms of a product, right? Right, we can just divide by multiplying by the reciprocal, which is what this is. And then we would use the product rule, and which is a perfectly okay way to do it. But it is not necessary, because this will sometimes take a lot more work. We do have a formula. Actually, if you use this, right, if we look at this, do the product rule with it, we actually get another formula, and it will be the quotient rule. So the quotient rule is really just the product rule for the second thing being 1 over g of x. But nevertheless, it is a nice formula to have when differentiating. And so the mnemonic that I learned is low d high minus high d low over low squared. And so what that means, we have low, the first, the bottom function, g of x. So low d high, so low times the derivative of the upper function, the numerator. So f g of x times f prime of x. Then minus, so low d high minus high d low, which would be f of x times g prime of x. f of x times g prime of x. And all of that over low squared. So g of x squared. Okay, so this is the product rule, this is the quotient rule. We're not going to be using the quotient rule as much. The product rule we will be using, especially we'll talk a little bit later about integration by parts, which is what we will. And that's undoing the product rule, so we're going to want to really know the product rule. So now I've just got two quick other rules. Make sure you have that down. If you don't, rewind and get it down. Unless if you're familiar with this, that's perfectly okay. That's actually great. So now I've got two more rules. Right. The first one is just the derivative of a specific function that we didn't really cover the derivative of yet, and that is the natural log of x, right, ln. And what is the natural log of x, or what is the derivative of the natural log of x? And you can actually, if you plug it into the difference quotient, do a little bit of algebra, you would find something that has been well known to mathematicians in calculus, something that has been derived before, right? The derivative of the natural log of x is fairly miraculously 1 over x, which is really, really interesting. This is just something you can sort of memorize it as a definition, or if you want to know, in the description, both for the quotient rule, I'll have a proof of that, but also a proof of this. I happen to think it's really interesting, and it also ties in to the proof that the derivative of e to the x is e to the x. So that is the natural log. Now, the thing is, this is the only function, right, whose derivative, whose derivative is 1 over x. And that's just a nice note to show you. The power rule, right, d by dx of x to the n, right, we talked about this in the last video, d by dx of x to the n is nx to the n minus 1. And n, in fact, can be any constant, right? It's n, which sort of means integer, but in fact, for the power rule, it actually can mean any constant. So the last thing, and this is this one's going to take slightly longer. It's a pretty major rule, and you don't really need to have it mastered, but it will be useful. And if you've gone through Calc 1, this is probably something they've kind of hammered into your head. It's really important, and it is called the chain rule. Chain rule. And the chain rule is this. I've got u, right? U is a function of x, right? U is a function of x. And then I want to take the derivative, right? The derivative of f of u. And now this is, since u is a function of x, this is, a function of x. F of u is a function of x. But what I mean by this is, if I have something like, I don't know, e to the x squared, right? E to the x squared is a composite function, right? And it's not one of our basic functions. But if we say u is equal to x squared, this thing becomes e to the u. Right? And this is useful because we can differentiate e to the u with respect to u, and we're going to use that in trying to differentiate e to the x squared with respect to x. Right? So, this is what I mean. It's where where I'll have that arrow there just to show that this is like the same thing using u equals x squared, right? And so the u substitution here, the u equals x squared, is just to make a composite function into a simple function. Just like if I had, you know, a root of x squared, right, square root of x squared minus 3, right? If I used u equals x squared minus 3, this would be the square root of u, or u to the 1/2, which we can differentiate using the power rule, right? So you can hopefully see why that would be useful. You know, you take this embedded function, x squared minus 3, and then you turn, that is u, and then we turn that into something we can differentiate. And so what we're going to do, actually, I'll leave that up here. The chain rule states that the derivative with respect to x of f of u is the derivative of f, and I'm just going to leave off the of u or of x. So the derivative of the function with respect to u, and then times, right, times what's called, some teachers will call it the correction factor, some will call it the chain, hence the name chain rule. The chain, the correction factor here is times du dx. Now there's a lot of interesting things we can do with this, and the chain rule is pretty beautiful, and you can also see kind of a derivation of it. These du's cancel out and we just get df dx, which is what we want, right? But if this formula doesn't make a ton of sense to you, right, let's we'll do a few example problems with it. Now also, just for notation, sometimes this is written as f prime of u times u prime, where here the prime represents derivative with respect to u, and that's sort of shown it's f prime of u, so it's the derivative with respect to u, then times u prime, or u prime of x, but u prime is the derivative of u with respect to x. Alright, so let's tackle a few practice problems. So I've got the derivative with respect to x d by dx of, well, let's do what we had before, e to the x squared. Well, if I let u equal x squared, right, I get, this becomes e to the u, and the derivative of e to the u with respect to u is just e to the u, right? And then times the derivative of u with respect to x. Well, u is x squared, so the derivative by the power rule is 2x. So the derivative with respect to x of e to the x squared is 2x e, right? 2x e to the u, but u is x squared, so 2x e to the x squared. So you can see we've got the derivative of this with respect to u, or with respect to x squared, and then times this correction factor, the derivative of the embedded function here. And this is sometimes called, the 2x part is sometimes called the chain. Alright, so let's try another example, and then I'm going to do one brief generalization, or it's sort of a formula that has to do with a specific case, a general formula that has to do with a specific case of the chain rule. Alright, so now, let's see. Now we can do, say, I have this example too, the square root of, let's say, x cubed, right? We'll change it up a little bit, x cubed plus 2x, x cubed plus 2x plus 1, right? And I want the derivative, right? The derivative of this. Now what I'm going to do is I'm going to let u equal x cubed plus 2x plus 1, right? So now I have, right, this becomes, and I'll do it in a different color here, this becomes the derivative with respect to u of the square root of u, but that's just u to the 1/2 power, right? And then times, this is multiplied by the derivative of u, right? But we can just do that easily right here. The derivative of u is going to be 3x squared plus 2, right? And now we know that the derivative of u to the 1/2, we take this power down, so 1/2 times u to the negative 1/2, so that's 1 over 2 root u. So this is, so this thing, right, this is 1 over 2 times, sorry, I'll rewrite that. 1 over 2 times the square root of u, right? The square root of u is also in the denominator there. You can see that's, right, 1/2 times u to the negative 1/2 power. That's just a different way to write it. And then if we multiply this by 3x squared plus 2, our final answer, right, the derivative of the square root of x cubed plus 2x plus 1 is 3x squared plus 2 over 2 root u. But what is u? Right? U is x cubed plus 2x plus 1. So I, put the function back in. So I get x cubed plus 2x plus 1. And I know I sort of ran out of room there, but hopefully, I know you can't read that, but you know what I'm saying here, x cubed plus 2x plus 1. Okay, so hopefully you have all this done. I'm going to erase it just for one final point in this video. One final point. And the final point that I would like to make is I've got a function, right? And actually, I'm going to start it off with this. I'm going to say A is a constant. All right, so A is a constant. And I want to take the derivative with respect to x of some function of ax. And what that would mean is, right, this would look something like e to the ax, or the natural log of ax, or even the square root of ax, right? The embedded function is just a multiple of x, right? A constant multiple of x. So I want to take this derivative. Well, what do? Well, this is f prime of ax. It's just the derivative, right? The derivative, and then you plug in ax times the derivative of ax, and the derivative of ax is, right, pretty easy. It's the constant coefficient rule and the power rule. It's a, right? So I'll write it like this. dy dx of f of ax is equal to a times f prime of ax. So it's just like taking the derivative, right? We're just taking the derivative of the function, we're plugging in ax, but then this a, the a that's attached to the x here, just gets brought out. So, for example, the derivative of e to the ax, right, is a e to the ax, because the derivative of e to the x is e to the x, so, right, this is just a nice shortcut to when the embedded function for the chain rule is just a constant multiple of x. One more example, hopefully you've got this, right? Look at the natural log, right, of ax. What's the derivative? Now this is actually fairly interesting, and you can make sense of this using properties of logarithms, but natural log of ax, right, the derivative, right? This is a, because you bring that a out, right? And then the derivative of the natural log is 1 over x, so we get a over ax. The a's will cancel out. Apparently the natural log of ax has the same derivative as the natural log of x, and see if you can figure out why that is with the properties of logarithms. So that's basically it. I do have one other really quick thing too for just as a reference, a function that you may not quite understand how to apply the chain rule to. And that would be something like 2 to the x, right? Or even, in the general case, still having a be a constant a to the x, right? And so if I want the derivative of this, right? Well, I know that e to the natural log of a, right, is a. This is sort of I consider this a definitional property of the natural log, right? And I also know that e to the natural log of a raised to the x power, right, is just a to the x, right? And this is also, right, just taking this, we can multiply, right? If we have a power raised to a power, we can just multiply the powers, right? So this is e to the x times the natural log of a. And since a is a constant, the natural log of a, right, is a constant. And this is just a basic application of the chain rule, right? This is the derivative. Hopefully you see how I got this. If you didn't, rewatch it a few times and review your properties of logarithms. It should be fairly easy. The derivative of, this is the same as the derivative of e to the x times the natural log of a, right? And the natural log of a, right, is our constant multiple of x that we've got. So this is just, right, our multiple natural log of a times e to the x ln a, but e to the x ln a is just a to the x. So it's the natural log of a times a to the x, right? Just sort of skipped a step, but it's the natural log of a times e to the x ln a, which is natural log of a times a to the x. And natural log of a is a constant. So if I asked you what the derivative of 2 to the x is, it would be the natural log of 2 times 2 to the x. That's just a little application of this that it's pretty easy, but you sort of just have to think in terms of changing a function like 2 to the x, right? Changing a function like 2 to the x into the natural exponential, e to the ln of 2, all of that raised, or e to the ln of 2 times x, right? You can also look at logarithms of different bases, which I'll let you do on your own. Just look up the change of base formula if you don't know it, and you should see pretty easily how you would take the derivative. It doesn't even require the chain rule, how you would take the derivative of, for example, the common logarithm or the log base 9 or anything. All right, so this is just a surface video on how to take derivatives of a bunch of different functions, products, quotients, and then the chain rule embedded functions, which a lot of functions are going to be embedded. So yeah, hopefully this makes a bit of sense to you, and you should really understand the chain rule. We are going to be using it a lot, and the product rule too. The quotient rule not so much, but it's pretty easy. All right, see you in the next video.